Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at two sections in Chapter 2. Section 2.2, which deals with mixtures, and 2.3, which deals with elements and compounds. First off, classifying mixtures. Well, what is a mixture? A mixture is a physical blend of two or more pure substances. So separates and makes it very different from a pure substance, because remember, a pure substance couldn't be separated by physical means. So if we take pure substances and physically blend them together, we can also physically separate them. Now, there's two different types of mixtures that we're going to look at. The first would be a heterogeneous mixture, which is a non-uniform composition mixture. So if we put sand in water, the sand in water, no matter how much you shake it, once you stop shaking it, it's going to separate into different compositions in different regions inside the container. So it's not uniformly mixed together. So sand and water would be a good example of a heterogeneous mixture. Hetero meaning different. So it is a different composition throughout. Now, homogeneous mixture, which has the synonym solution. So if you ever hear the term solution, we're talking about a homogeneous mixture, is a mixture of uniform composition. So the physical substances that we've mixed together mix uniformly. Now remember, this is not a pure substance. A pure substance has a definite composition. Uniform is not the same as definite. If it's evenly mixed together, then it's uniformly mixed. So it has an even mix, but it's not the same throughout. So it has a varied composition. So mixtures have a varied composition. Both heterogeneous and homogeneous have varied compositions. But heterogeneous is non-uniformly mixed, and homogeneous is uniformly mixed together. Now, a phase is a part of a system with a uniform composition. And phases are a little bit different between homogeneous and heterogeneous situations. Now, the term phase is used to describe any part of a sample with a uniform composition and properties. Now, when we have a homogeneous mixture, since it is uniformly mixed together, we have a single phase of uniformity. So homogeneous mixtures consist of a single phase. Now, when we have a heterogeneous mixture, because it's not uniformly mixed together, we're going to have regions within that have uniform composition. So a heterogeneous mixture is going to be composed of two or more phases. A good example of this for a heterogeneous mixture would be oil and water, like in, or I should say vinegar and oil, like in salad dressing. No matter how you shake it, once you stop shaking it, it's going to separate into an oil layer and a vinegar layer. And within the oil layer, you have a uniform composition. Within the vinegar layer, you have a uniform composition. So we have two different phases that this heterogeneous mixture separates into. Now, if we can physically blend pure substances together to make a mixture, then we should be able to physically separate. So what are some different types of physical separation techniques? Well, the first and most basic and most commonly used in the lab would be filtration. And that's where we separate by passing it through a barrier. So a filter paper would be a good example of this. And this is the same kind of principle that you use in the making of coffee. You need to separate out the coffee grounds from the coffee solution, and they pass it through a piece of paper to do that. So filter paper would be an example of a barrier. Now, when you look at a piece of paper, it doesn't look like it has holes, but on the microscopic level, you definitely have holes between the fibers in the paper. A large substance like sand would be trapped and held back on the other side of the barrier, whereas substances like water or things dissolved in water would pass right through those small holes. So filtration, or in this case, paper filtration, would be a good way to separate a mixture like sand and water, where we have a larger substance like a solid and a smaller substance like a liquid, and substances dissolved in the liquid. Now, if we dissolve salt in water, it would pour right through, and the salt would not be held behind in that paper barrier. Now, there are other high-tech types of filtration, reverse osmosis filtration systems and so forth, that may be able to separate out dissolved particles, but normal paper filtration be a good way to separate a solid from a liquid. Now, a related idea that sometimes when students think about this, they don't realize, oh, that's just filtration. If you had larger pieces of gravel and smaller pieces of gravel, and you poured them onto a screen like chicken wire or something with holes within it, and you shook it around, the larger pieces would be held behind, whereas the smaller pieces would drop right through the chicken wire. So a screening is an example of a filtration technique. You're just passing through a barrier with larger holes in it. Now, another type of separation technique that works with solids and liquids like sand and water, but more importantly, it works with liquid mixtures or things dissolved within liquids would be distillation. So distillation uses differences in boiling point to separate liquids and solids or liquid and liquid mixtures. Now, once again, this is a physical separation technique. So we're not chemically doing anything. We're just physically separating the components. Like in filtration, where we were physically separating something like water from sand by passing it through a barrier. Now, in a typical distillation apparatus like you see here, first you need a source of heat because one of the things, if we have substances with different boiling points, as we heat them up, we're eventually going to hit the boiling point of the lowest boiling point substance first. And at that point, that substance is going to go from a liquid to a gas. So we need a heat source to do that. So in this case, it's a Bunsen burner, but it can also be an electric heating mantle. And what we've got is tap water, which is water with dissolved particles within it. It may also have some dissolved liquids in it as well. And as you heat it up, eventually it's going to hit the lowest boiling point substance. Well, if it's the only liquid is water with dissolved chemicals or other solids in it, the lowest boiling point substance is going to be the water. So once we hit up around 100 degrees Celsius, the liquid water inside the container will start to be transformed from a liquid to a gas. But the other particles, which have higher boiling points, are going to be left behind. And as that gas rises up in the air, it's going to move out through this device. Now, the problem is it's at a very high temperature, which water is going to exist at the gaseous state when it's above 100 degrees Celsius. So at some point in this process, we need to cool that gas back down to recondense it back into a liquid. So in this particular case, what we have is cold water coming in to our condenser here, and really the liquid that's coming inside isn't connected to that inner tube that goes all the way through the condenser. So it makes a jacket of water around it. And as this fills up with water, that cool water will condense the gases that come down through, converting it back a liquid so it can be collected over here. So if we had salt dissolved in water, the salt, which has a much higher boiling point than 100 degrees Celsius, is going to be left behind over here in our container, but the water would move through. Now we can also separate a mixture of something like rubbing alcohol and water. Rubbing alcohol has a lower boiling point than water does. So before we get to 100 degrees Celsius, once we get to the boiling point of the isopropyl alcohol, the rubbing alcohol, that's going to be coming through our condenser and then dripping out the far side. Now in this particular case, since the rubbing alcohol is a lower boiling point, it's going to come across first, leaving the water behind. Now if we heat it up eventually, we would push through all of our rubbing alcohol. We could move that off to the side, and then you'd notice the temperature is going to start to rise again until you get to the boiling point of water. And at that point, what's going to come through is water. And we will have separated at that point our rubbing alcohol from our water solution. So that's a distillation apparatus. It uses differences in a boiling point. Filtration uses differences in size, which is a physical property of the substance. And in a distillation, we're using differences in boiling point. Next type of separation technique is crystallization. And this is something in college chemistry I did in a number of times in organic chemistry labs and so forth. When you create a solid that is in a liquid, and you recrystallize the solid out of the liquid, it actually grows with very high purity. So the solid that gets created in this crystallization process that you can see in the flask over here on the right, this is a very high purity crystal. And if you pass that through a filter paper, the crystal would be left behind, or solid would be left behind, and the liquid would be separated from it. And that crystal ends up being a crystal of very high purity. So it's a formation of a pure solid particles from a solution. This is one way in which pharmaceuticals can often be created. So you can end up with a very high purity chemical that's used in the pharmaceutical through a crystallization process. And the last one we're going to look at is chromatography. Now, this is an image of paper chromatography, which is one type of chromatography. In chromatography, you separate components of a mixture based upon the speed with which they move across a medium. So basically what has happened here on these images is in the first one, they probably took something like a black overhead marker and then make a colored dot here at the bottom, and then they hang it in water. And what's going to happen is that dot is above the water, And as time goes by, the water is going to start to wick up the piece of paper. And it's going to carry with it the dyes that are inside the black ink. Now, those dyes have different sizes to the chemicals. And what happens is the smallest chemicals are going to move through the fibers of the paper more quickly. And you can see right here where this blue color is, those would probably be our smallest chemicals inside the material. The larger particles, which are going to move through more slowly, are then going to get separated from those. So we've literally by just taking and letting water pick it up and move it through a piece of paper, we've ended up separating our black into our various colors that you see. So this would be an example of one type of chromatography, paper chromatography. The different chemicals that make up the dye inside the black ink are going to move at different speeds through the paper fibers. Now, chromatography can get very high tech, and there's different types of chromatography. But in essence, if you have a mixture of substances and you move them through some medium where some of the chemicals move more rapidly than others, what comes out the far side is going to have those chemicals separated. And there's liquid chromatography, there's gas chromatography, there's a number of different very high tech techniques to do different types of chromatography using different types of situation. So those are our four fundamental types of separation techniques that we're going to talk about this year from time to time. Now, next section 2.3 gets into elements and compounds, our pure substances. An element is a pure substance that can't be separated into simpler substances. It can't be separated chemically or physically. Now remember, mixtures are physical mixes, so they can be physically separated, and that's what separates them from pure substances like elements and compounds. Elements and compounds themselves can be separated by whether they can be separated chemically. Now, on the periodic table, we've got more than 90 elements. Well, 91 of them are naturally occurring that we can find in the world around us. The rest of them that are on the periodic table are synthetic, man-made elements. Typically, those are going to be very unstable substances, so they're radioactive, so over time they decompose and break apart into other things. But we really only have 91 naturally occurring elements, and then a number of elements that have been synthetically made by man. Now, when we name an element, or write its symbol, I should specifically say, we always use the same format. The first letter in the symbol is always going to be capitalized. The other letters are going to be lowercase. Now, compounds, on the other hand, are two or more elements that have been chemically combined. Well, if they've been chemically combined, they can be chemically separated. And once again, they can't be physically separated, neither can elements, because physically separated things would be mixtures. Now, unlike elements which have a fairly limited number, when we put together and bond together elements to make compounds, we can make many, many different types of compounds. Now, this number is probably on the low side because each year scientists have either synthesized or found in nature 100,000 new chemicals a year. So very rapidly, scientists at universities and colleges, as well as in business settings and labs, are isolating and manufacturing new chemicals all the time. Now, when you write the symbol for a chemical, we need to describe the elements and the quantities of those elements that are listed in it. Now, these are three common everyday elements you have at home in the kitchen. H2O is obviously water. NaCl, I think most of you recognize as table salt. So what's C12H22O11? Well, that's sugar, another common substance. So that's actually sucrose. Now, the symbols represent the elements, and the subscripts, you think they represent how many atoms of each element we've got, but that would only be true if we have one of the substance. So one of those units. So a more general definition when we have a whole batch, because when do you have just one of anything? They're so incredibly small. We typically have billions and billions and billions and billions of them together. So a better way to describe what the numbers mean is to say that they're the ratio or the proportion in which the elements are found in the compound. So if we had one sucrose molecule, yes, we'd have 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. But if I had a container of sucrose, it would still be true that I would have twice as many hydrogen atoms as I have oxygen atoms, and they would be found in a ratio of 22 to 11 in there. So if we knew how many total molecules, we could calculate how many individual atoms. But it's still true, no matter how many there are, that this would always be the proportion, 22 to 12 to 11 within the solution. Now, if we put those ideas together, we can basically classify matter into various categories. So what we're really going to do is really just recap what we've already said. Now, first of all, matter is anything around us that has mass and volume. So all the stuff around us that we can touch and has mass and has volume. Now, to separate matter into the first two categories, we ask the question, can it be separated physically? If the answer is no, then it's a pure substance. If the answer is yes, then it's a mixture. Remember, pure substances have a definite composition. Mixtures have a varied composition. Now, there's two different types of pure substances, and what separates them is whether they can be chemically separated. Elements cannot, and compounds can. So examples of elements, carbon, gold, iron, and the others on the periodic table. Compounds, there'd be many, like water and sodium chloride. Now, if we have a mixture, the way to separate our two different types of mixtures is whether the composition is, or whether it's made up and uniformly mixed together or non-uniformly mixed together. Homogeneous substances are uniformly mixed. Air would be a good example of a uniform or homogeneous mixture. The air inside a room, at the top of the room, at the bottom of the room, is essentially the same exact mixture. It's uniformly mixed together in the room. Dissolved particles in water, so anytime you dissolve something in water, they will uniformly mix together as well to make homogeneous mixtures or solutions. If it is not uniform in composition, like let's say I had sand thrown in water or muddy water, or even a barrel of pens and pencils mixed together, no matter how much you shake them, they're not going to be truly uniformly mixed together. So they would form heterogeneous mixtures. A good example of a heterogeneous mixture is like vegetable soup or river water. Those would be non-uniform compositions. Now, let's go through and take a look at some of the things we just looked at with kind of a invented group of substances here, or invented pieces of matter here, to see whether we can understand what is what. Now, we have four things listed on the right. We got AAB, AA, or ABBB, and so on. Now, which of these would represent elements? Well, an element has to be a definite composition, and it has to be the exact same throughout, and you can't chemically break it apart into anything similar. So that would be substance, or not substance, but the second form of matter that we have over here. Now, which of these would be compounds? Now remember, compounds are two elements chemically fused together. So they can't be physically separated, they can only be chemically separated. Well, that would be substance 4. The A and the B here are fused together to make an AB. Now, which would be a homogeneous mixture? Well, homogeneous is when they're uniformly mixed together. Well, in situation 3, we've got AB, AB, AB. It's a varied composition, so it's definitely a mixture, but it is evenly mixed together. And then the heterogeneous mixture, a non-even mix, which would be situation number 1. Now, which of these have definite compositions? Remember, definite means the same throughout. Well, situation 2, it's all A, it's the same throughout. In situation 4, it's all AB fused together throughout. So they would have a definite composition. Which one would have a varied composition? Well, situation 1 and situation 3. They're not the exact same thing throughout. They're not definite in composition. Now, which one would be uniformly mixed together? Remember, everything with a definite composition has to be uniformly mixed together, along with everything that is evenly mixed together. Well, that would be situation 3 and situation 2 and 4. 2 and 4 because they're definite composition pure substances, and 3 because it is uniformly mixed. So remember, all pure substances are technically uniformly mixed together as well. It's just they have a definite and uniform composition. Next section, we get into the periodic table of elements. So we're looking more closely at our list of elements. Now, one of the things, and we're going to get more into the periodic table later, but at this point I want you to have a rudimentary understanding of how we put together this table into rows and columns. So a row on the periodic table, an across, is called a period. And there's 7 different periods on the periodic table. I know it looks like there's 2 down at the bottom, but they're actually within periods higher up on the table. And then a column on the periodic table is known as a group or a family. Now, a family is a group of people that share some commonality. So a group or a column on the periodic table are often things that are similar to each other. Now, elements in the same group then are going to have similar chemical and physical properties. And that's an idea that we're going to utilize in a number of different situations in chemistry. So our columns on the periodic table are groups or families, and those are elements that have some similar chemical and physical properties. Now, we call it a periodic table of elements. So what does periodic mean? So how is the periodic table of elements periodic? Well, what happens is, as you wrap around the table and come back to the same column, you have a periodic repetition of the pattern in similar chemical properties. So when you wrap around and come back to the same column on the table, you have things that are chemically similar to each other. So there's a periodic repetition of things with similar properties on the table. So when you take a look at a periodic table, a row would be in a cross. So this is the third period of the periodic table. Now I'd mentioned that two of the rows on the periodic table have been pulled out. This one right here is actually in the periodic table in that position, and the one right below it is actually inside the 7th period. So remember, this is actually in period 7, and this is actually in period 6. If we put them there, they'd be like either make a super wide periodic table that's not convenient, or they'd all stack on top of each other, in which case we can only see the top element in the stack. So we pull them out and put them across the bottom for simplicity's sake. So periodic table has 7 rows or 7 periods. Now it also has 18 different columns. So we've got 18 different groups or families on the periodic table. And what I just highlighted is actually in group 17. Those are what are known as the halogens. And halogens are something that throughout the year we're going to talk about from time to time. And that finishes our second day of notes over chapter 2.